First I'd like to say a quick thank you to Martin and to the other speakers for a very enjoyable week of lectures. For those of you I hadn't had the chance to speak to yet, my name is Tim Rogers. I'm a student at King's College London, and I'm going to demonstrate to you today another technique to calculate the density of states, or spectral density, eigenvalue distribution, whatever you want to call it. In this case, with sparse random matrices. So we essentially take a random matrix and we delete almost all of the entries, and we keep only finitely many per row. And this work I undertook in conjunction with my supervisor Isaac and two colleagues of ours, Kujin and Reimer, who is in the audience today. Fortunately for a Friday afternoon, this is a wonderfully simple technique, so if anything isn't clear, please stop me and ask questions at any point. So, surprise, surprise, there's a beginning, a middle, and an end. I guess the real point here is that if you're interested in this, if you want to read about it in more detail, we have a paper on arXiv. So if you write down the number, you can find out about that. So, a quick introduction, although I'm preaching to the converted here, you all know all this already, so perhaps I'll concentrate mainly on the sparse matrix aspect. We had a little brief discussion yesterday about the conditions necessary for a matrix to have a density, or an ensemble to have a density of states governed by Wigner's law. And one of the easiest ways that we can move away from Wigner's law is to make the matrix sparse. And there are many more complex spectra possible when you do this. And matrices of this type are quite important in disordered systems and spin glasses, and they've been studied quite extensively. And the problem of the eigenvalue distribution has been studied using the replica trick, which is a technique from spin glasses, and also using the supersymmetric methods, a paper by Fyodorov actually. And they arrive at the saddle point equation, which in principle is quite difficult to solve. And this has led to various approximative schemes. But it's important to note that an exact solution to this equation is still not yet known. So, quick set of definitions. If we have a single matrix A, and we have eigenvalues lambda IA, we can turn this into a density just by placing weighted delta peaks at each of those locations. And Wigner's law, as we've met already, and here's a little histogram showing you what that looks like. So it just randomly generates some matrices and produce a histogram of the eigenvalues, and this is what you get. For sparse matrices, this doesn't hold, as I mentioned before. So Wigner's law here is a dotted line, and the blue line is a histogram I've generated by making Poissonian random graphs. So what I mean by that is I've taken a large empty 1000 by 1000 matrix, and with a probability 3 over 1000 for every possible place I could place a value, I've entered a Gaussian random variable. And when you do this, you get statistics that look quite different from...
Hopefully keeping it symmetric.
Yes, keeping it symmetric, yeah. If you don't keep it symmetric, you get something completely different. And we study this case using techniques from the theory of spin glasses. So this is a by no means comprehensive review of these are just some of the major works in the field. Edwards and Jones showed how to push this problem into one that could be phrased in the language of statistical mechanics. Rogers and Bray actually did consider sparse matrices, and also there's the supersymmetric approach. There's a good paper by Fyodorov and Merlin, and they go on to calculate the level correlations as well. But as I say, the saddle point equations in the general case and the sparse case are deemed too hard to solve. And there are approximative schemes called the effective medium approximation, the single defect approximation. These aren't actually due to Coulian-Delot. I think Birioli and Monosson more, but it's a very nice review paper in 2002. So we're going to revisit this problem with a fresh pair of eyes using something called the cavity method, which I'm going to explain to you now.
Could I ask?
Yep.
I thought Kasten had done some work in this area also. Is that not true? Or?
That's quite possible. I'm afraid I'm not aware of it.
Is it precisely the same one?
I think so.
Yeah. When?
Maybe even preceding some of these references. It was. It's a little different because I think he was talking about a random graph with fixed valence.
Yep.
And
it's fixed.
Fixed valence.
This is different because you see it fluctuates. It's very
that will be like a tree in some sense if it's fixed.
Fixed valence.
Yes, it will be locally like a tree with regular.
And how is you have variable valence, or I thought you had fixed valence too, but you had a random variable.
Random. It's random.
Random valence.
Yep. So we've seen before some of these manipulations. This is another representation for the density of states. It's not hard to check that this is true. I'll take it on trust if you don't know this already. And I'm representing this here using with what I'm going to call a partition function. It's not really, because this measure is complex, but it's a really nice metaphor to have, and the cavity method was originally developed to deal with statistical mechanics, and so we've kept all of that leftover language, and it's quite nice to think about it in those terms. So this integral really just represents the determinant.
So is that actually the expectation of rho A lambda, or is it actually equal to this middle line here?
So the square brackets.
No, on the left-hand side. Rho A lambda times the top's a random object, right?
Yes.
Is it still random in the second line?
It is, yeah. The randomness is built into the partition function by the dependence on A.
Oh, okay.
And A is the random matrix. Okay. But I mean, we can consider a single fixed instance, so we can imagine that we've drawn this random matrix and now we want to diagonalize it. And so we can interpret this in terms of a graph determined by A. So a graph has an adjacency matrix, and in turn, with any random matrix, we can associate with it a graph simply by drawing, if it's an n by n matrix, we can draw n points. And whenever there are a non-zero entry aij, we draw a line between those 2 points and we weight it with the value of that matrix element.
But what is your choice for non-zero entries? It's just fixed, or you allow them to be random?
So it's anything. I mean, we consider this matrix, this is a quench disorder, if you like. This matrix has been generated. We know the values, and we're now going to draw the graph of it.
Oh, okay, fine. This graph is clear. I just want to know what is for the A.
And so we're going to call
Can I
these.
ask one thing? Compared to Fyodorov, I'm missing a factor of I. So
Yeah, so this really ought to be represented as a Fresnel integral, I guess.
So it goes over contour, practically the same.
Yeah, I mean, it's just twisting the contour in the complex plane, I guess. Yeah.
It's hidden in integral. It goes
Yeah.
along imaginary axis.
Yeah, if you like, yeah, we integrate along the imaginary axis rather than the real. Yeah, yeah. It's just hiding some complexity from the audience, I guess. Okay, and we're going to treat the integration variables now. We're going to imagine that they live on this graph, and that they live on the vertices of this graph indexed by their place in the matrix. Okay. And so the partition function that we had on the previous slide now appears in a kind of a Gibbs-Boltzmann reminiscent fashion. So when we actually look at this and we go back to our expression for rho and consider what is this object that lives inside the square brackets, it's not a difficult thing to check. Again, if we go back to our partition function, that actually this is just the average of the square of the spins. So if you like, so my angular brackets here, I'm referring to the average, if you like, in this integration defined by the probability distribution above. Remembering that probability distribution, average, none of these terms are really correct.
So it's still random, but these brackets mean that averaging with that weight above, right?
Yes.
But this weight itself is still random because it depends on random matrix.
Exactly, yes. But it's quenched, so,
Yes.
okay.
And as I understand it, there are like two levels of randomness in the quenching.
Mm-hmm.
You're going to do a whole bunch of deletions.
Yep.
You're going to add in maybe a small number of non-zero guys. And is that always fixed, and then the averaging is over? Once you fix that, is now the averaging Gaussian for each of those non-zero guys, and you always fix the first one?
So I guess the thing is that the randomness here is kind of a distraction. If I simply write down a matrix, I can apply this technique to it. However I choose to generate it. And when we come to solving it, we can solve these things numerically, and when we come to do that, we're going to, however you generate it, you can apply this to it. If you later want to do an ensemble average, then you have to plug in whatever technique you're using to do this. Okay. So looking at this, we see that this measure P, we don't need to know it in its entirety. The important part is how it behaves as a marginal on each of these sites. And the cavity method offers us a way to compute this without having to compute the entire thing. So here is the caveat, the important thing. We need to assume that our graph that we've drawn based on this matrix has no short loops. And I mean loops in the physics sense or cycles in the mathematics sense. So in other words, locally it looks like a tree. So here we can see, so a site I really represents a row. And the variable lives on that site. And clearly here, the joint distribution over the neighborhood I refer to with this sort of partial symbol, it's not going to factorize. These guys are correlated, these variables that live on the neighbors are linked by I, so they're heavily correlated, their distribution doesn't factorize. However, and this is the trick, if you were to remove I, these guys are no longer linked. Or rather, if they are linked, they're linked by an extremely long cycle, and we can ignore it. And so we can assume...
The long means logarithm of size of the matrix.
Sure, or any, just so long as it grows, log, 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 you know, so long as it gets...
Typically it's log n.
Yeah, so for a Poissonian random graph, cycles are log n. And so in the infinite volume limit, we can ignore them.
Hopefully.
Hopefully, yeah.
Not clear.
Not clear.
Well, so these P's with a superscript I refers to the system that I've created by removing I from the equation. And in this situation now, this joint distribution over the neighborhood does factorize. And if one were to know what these P, L, I's were, if we knew how these neighborhood variables behaved, when we returned I to the system, we could treat those guys as almost boundary conditions for the variable that lives on I, and we can extract the behavior of I from them.
Is it kind of self-consistency then?
We will eventually arrive at a self-consistent equation, yeah. So here Pi is the real marginal of I, and it depends on the basically the relevant part of the Hamiltonian averaged over what the distributions, which we assume to be known on the neighboring variables, are in the absence of I. So the question boils down to how can we compute these neighboring cavity distributions?
So when you do this, is this equivalent to studying the density of states on a sort of a random Cayley tree or not?
I think so, yes.
Yes, basically, yeah, yeah.
Effectively, it is attempt to calculate for a tree, randomly branching.
True. It doesn't have to be a tree, but it has to have some tree-like structure. So maybe it comes in big clumps and you can remove a clump at a time, but you have to do a different analysis for that. So this simple example is just
for a tree. It will be certainly correct.
For a tree, for a finite tree, this is exact.
If for a tree, it's exact, and
Yep.
and you'll get the same answer. I mean, the answer you produce will be the same as if it were a tree, correct? To the random branching.
Yes, yeah. So the question is, how can we compute these cavity distributions? Go on.
This I is the column, it's the row of the matrix, and L is the columns.
So I'm thinking now about the graph picture, where I've taken my matrix and I've turned it into a graph by...
Is it related to your matrix?
Sorry?
How is this indices related to your matrix?
So it's rows and columns, yeah. So an entry Aij refers to the link between the site I and the site J. Okay. And here's the clever part. What you can do is imagine what would happen if you were returning I, but you didn't reinstate the link to one of its neighbors. If you perform the same process now, what you will in fact have calculated is the probability distribution of the variable xi in the absence of the neighbor j. So this equation at the bottom is now a consistency equation on these cavity distributions. If we could solve this equation, we could solve for the real distributions, we could find the real second moments.
So basically what you say, that you are very deep in this tree.
Yes.
And therefore, basically you require that when you delete one site and then recalculate the rest, it's the same as influence of this rest, and so it's indeed self-consistency.
Yeah.
Which
Okay.
hopefully again should hold for distribute. You impose it not for moment, for the distribution, right? Okay.
Okay. So if we can solve this, we can recover the density of states quite quickly. And it turns out, with some degree of just staring at it, that this admits a very nice, very simple Gaussian solution. We can simply plug in a zero mean Gaussian parameterized bivariance. Plug it in, do the integration. It's a simple Gaussian integration we've seen a couple of times already this morning, I think. Compare the left and right hand sides, and we arrive at a consistency equation for the variance.
I want to come back to Martin's question. What about the I?
Heavens. Go on.
But the most important part is already.
Yes, I get the maths is done. So we can, go on. Sorry.
What about the I again? I mean, so when you do these calculations, do you take into consideration the fact that you have to take a contour, which is?
So I guess the most relevant place where this abuse of terminology and calling these things probability distributions comes in is in the fact that those variances I just showed you have a big imaginary part. So this is a contour integration, but taken over the imaginary line.
To make it clear for myself, is it only one tree, or you can have like several trees which are disjoint?
They can be disjoint, certainly. So the matrix might require that. If I write a matrix down, it may turn out that it has a disjoint part. It may not. This doesn't matter.
But you see, your equations, in fact, I think they are just what appeared when people studied. I realize it now. Trees just in the right self-consistency equation. It's like
exactly.
Taudis and Anderson. Basically, these are the same. Self-energy they called it, or something like that. Because you never, you see, there we consider the difficult part is just to perform adequate average over the disorder. Because you just wanted to give consider given metrics.
Yep.
So, okay, then I realized what it is.
We can average later.
Yeah.
Okay.
I see.
So we're back in business. So these deltas have an imaginary part. So these are not real probability distributions. We are integrating differently, but it's nice to call them variants because they appear to behave in that sort of a way, and it gives a nice intuition on how to deal with this problem. Okay. So this is our consistency equation.
You could reinstantiate the imaginary part and rewrite everything. And get
Of course, yeah. Which I think is what you did in your.
Yeah.
That's how. So Reimer has a companion paper, not with the cavity method, but he arrives at a very similar set of equations, and he does do the integrals properly. Okay. So these were the cavity equations, and you can recover the real variances with a similar set of equations just by doing the integration as before. And so what really has happened here is the problem of finding the density of states has just been reduced to solving these equations. If I have a matrix, suppose its graph was a tree, and I wanted to know the density of states, all I would have to do is find a collection of these deltas that match this self-consistency equation. If I can, then I can recover the density of states straight away. So now, how can we solve these? So in some cases, we can actually do this exactly. A first check is to recover Wigner's law. I say recover. This is the worst slide in the presentation. It's slightly hand-wavy. It's just a test to see what happens when we grow our connectivity very large. So we're going to make these variables be identically distributed with zero mean and variance j squared over c. So c I'm going to take to be the average connectivity of a site. And I'm going to let c tend to n as n tends to infinity. So I'm taking this random tree-like graph, I'm growing it in size, and at the same time I'm growing the number of connections very large. And I'm hoping to approximate the Gaussian unitary ensemble this way. What happens when you take this limit? A couple of things. Firstly, each site has so many neighbours that removing one makes very little difference, order 1 over c. And secondly, the the neighborhoods become quite homogeneous. So we can replace this contribution with a simple average over the whole graph. And that the cavity equations we had on the previous slide become this simple quadratic, solve for the imaginary part, and we recover Wigner's law just like that. Okay. This isn't a proof of Wigner's law for Gaussian unitary ensemble. This is merely showing how it can arise from the equations we've derived here. We can solve exactly in some other situations. So a finite or a quasi-transitive tree has associated with it a finite set of these equations with a single solution. So simple cases can be solved algebraically. The example I've given here is the beta lattice, so which locally looks like a Cayley tree, but we don't include the boundary because Cayley tree has an extremely large boundary, and we'd like to ignore that.
But your self-consists, you already ignored it.
Exactly, yeah. So this doesn't apply to this. Although if I had a finite Cayley tree,
Yeah,
it's a
that's
tree,
what
I
it
can
is,
solve
yeah.
it. Yeah. And so this very colourful graph here shows what happens as you grow the connectivity of the beta lattice. And as it gets larger and larger, the shape deforms from the density of states of the line, the green graph, and it deforms into Wigner's law, or very close to it. And the question arises, what can we do in more complex situations? And one approach is a belief propagation algorithm. So we can initialize these deltas just to any realistic values. In fact, I believe there's certain situations where it should converge just for any arbitrary choice, but it helps if you pick them fairly realistically. And we can update them according to the cavity equations. So simply delete one and replace it with what its value ought to be based on the contributions from the neighbors. Do this for the whole graph again and again and again until convergence. And computer science people have done an awful lot of work on belief propagation algorithms, and they're very robust. And there's a really wide range of situations where they converge very quickly. From that, we can compute the real variances and recover rho simply from this formula. What does this look like when we actually do it? Well, if we return to the picture we had before, we can see that we can match the histogram recovered from direct diagonalization exactly with the results of the cavity method. In fact, in some sense, this is almost even better because the cavity method is analyzed at points, whereas this histogram is a histogram, it's just an average. So we can see places where there's a slight deviation. For instance, if you can see just here, the direct diagonalization is slightly higher up than what we would expect from the cavity method. That's caused by a delta peak that isn't at the place where we evaluate it with the cavity method. If it's an irrational value and we happen to not evaluate it there, then we won't see it. So the histogram is in some sense incorrect because it's merely a box around this, and the cavity method gives an exact solution. I've also compared this to
This exact numerical solution.
Exact numerical solution, yeah. So this comparison is also with a couple of the previous approximations, although again this isn't really a fair comparison at all. Okay. So a quick summary, what did we do? We took some standard steps to recast the problem into the language of statistical mechanics, and we stared at that a bit and noticed that in fact the single site marginals were sufficient to calculate this object. And we wrote consistency equations for those using the cavity method. We then solved those self-consistently with this nice Gaussian solution, which is characterized by a very simple set of equations. And we solved these equations for different ensembles. Or rather, they can be solved for different ensembles. I've only given you one example, but you name it, we can solve it almost. Simple cases you can do algebraically. If you want to do single instances, you can do belief propagation to a very high degree of accuracy. Another technique which I haven't mentioned so far is population dynamics. So those rules were rules for single sites in a single instance of quench disorder. If we want to think about how to do the average over the ensemble, which is usually the hard part, what we can do is imagine doing an experiment where I have a bucket full of matrices from my ensemble. I draw one at random, and from that matrix I draw a site at random. Now those rules are rules on the distribution of the variance of that site. So what were once rules for a single instance, for a single site in a single instance, you can now think of being rules governing the distribution of a random variable. You can write an equation for that, and you can use population dynamics to find a very large sample that satisfies that equation. I haven't got any results of that, unfortunately, for this case. So I should just mention before I finish, I've gone quite quickly actually, that as I said a couple of times before, actually, you don't have to have tree-like matrices. There are some other situations where we can apply this. One of the ones we looked at were covariance matrices. So if I take a tree-like matrix, or rather a sparse matrix, it doesn't even have to be square, so it no longer really represents a graph. And I multiply it with its transpose, I get a matrix whose graph is full of triangles, or rather it's full of cliques. And in fact, it still admits some kind of a tree-like decomposition, and I can place extra variables.
Sorry, just on a sec.
Go on.
B is to the right and A is to the left?
No, so B is just some sparse matrix.
Okay.
I take its product with its own transpose, I get a square matrix.
Okay.
If I look at what that graph looks like, it looks
cool.
nasty, it looks like this.
Yeah.
If I want to analyze this using the cavity method,
Yeah.
the trick is to place extra variables, one for each of these cliques. These are the boxes. And the boxes, the links here, mediate the behavior of the cliques.
But it should be done in somehow very clever way. It's not a simple thing.
It surprisingly is quite simple, yeah.
Well, I
Does
look
it-
at it this way. There's this formula, A equals B transpose B.
Yep.
You should write out this matrix product in the index
Uh-huh.
of the inner summation.
Uh-huh.
That is these squares, right?
Exactly, yeah.
Ah, I
Yeah.
see. This is.
So if you wanted to do this, if you were going to represent B transpose B in a Gaussian integral,
Mhm.
what this amounts to is doing 2 Hubbard-Stratonovich transformations for another set of variables.
And so you linearize it. You
Yeah.
write them off diagonal like blocks.
Exactly, yeah.
I understand.
Okay.
Okay.
Start trying.
Oh, that's interesting.
So this is another nice one. More generally, if this is a lucky artifact of the way this matrix was generated, really. If I just had some arbitrary matrix that had a tree-like decomposition, but that wasn't generated in this fashion, the trick then would be to group all of these things together and have a covariance matrix for that. And then you can write a consistency equation on covariance matrices and do the same thing there. Obviously, it then becomes a lot more computationally expensive the larger your clusters are, but it's still possible. So here's some results of the belief propagation algorithm on this type of matrix, again compared with something called the symmetric effective medium approximation. And again, very nice set of results, really. Sorry, what is lambda? So lambda is just the value at which we're evaluating the spectral density.
The spectral density for this BTB for A.
Yeah.
Right?
Yeah.
It's positive.
Yep. Yeah, so which is why it's all bigger than 0. Okay. And finally, I've only really spoken in this talk about symmetric real matrices. In principle, there's no reason why we can't apply the cavity method elsewhere. In fact, we have done this for just general sparse complex non-Hermitian matrices. So their eigenvalues invade the complex plane, and you have a density over the whole plane. In fact, looking like this. And details of this, obviously I haven't got time in this talk, but details are in a forthcoming paper. So here, unfortunately, the colors are reversed. The red grid is the results of many diagonalizations of these are Gaussian matrices where we don't require symmetry. And the blue lines are the results of, I think this time, population dynamics. Unfortunately, this isn't actually the most interesting picture. I couldn't get any of the others. You needn't necessarily get these nice shapes. You can get all kinds of donuts and diamonds and crosses and things that are very nice. But this will do. So there we have it gone.
Flipping back one to the,
Yes.
do you have any insight as to why this curve is so skewed?
Which?
Well, it's skewed to the left, so
Mhm.
it's not centered anymore. For example, like your other densities were.
But it's positive
Yeah.
definite.
Well,
It's
it's
not
positive definite.
be
Spectrum is
vanishing.
positive.
Okay.
So of course this is, and there's the Marchenko-Pasteur law, which is this shape but more regular. And then this is what happens when you delete most of the entries. It starts to push, and eventually this peak here will, as you move connectivity down, this peak will grow very, very high. Any other questions? I have a little time, so I've been very quick, I'm afraid.
Were you surprised to get the Wigner law?
Surprised in quite how easy it was, I guess. The derivation I showed here is far from rigorous. You can actually show, you can do this properly. For the sake of the presentation, I didn't. But I guess the Wigner law, it's not, we haven't shown the Wigner law for Gaussian unitary ensemble matrices. What we've shown is that tree-like matrices, as their connectivity grows, they belong to the same class of universality as those matrices that have the Wigner law.
In fact, there will be difference in the far tails. There will be almost semicircular law, and then some tails developing. As long as your connectivity is not literally proportional to some, not growing with the size of the matrix, but maybe huge but finite and goes. Always will be some tails. In fact, studied by Bray and Rogers, I think, in their first paper, by some instanton approach. And then recovered by this French, you mentioned them, but I forgot who they were. It was not written, but you mentioned.
Birioli, Monosson?
Yes. Okay. In their paper also they studied. They are these tails are dominated by abnormal sites, where abnormally you have a lot of connections.
Hubs,
Do you have any insight into this? Why the spikes appear heuristically?
The delta peaks. So it's easier, perhaps, if you think about, rather than Gaussian variables, if we have plus and minus ones, if you have Bernoulli variables. Then any finite tree will occur very often in a large enough matrix, and you could diagonalize that yourself, and you could work out what the eigenvalues were, and you would see that very, very often. And moreover, if that tree was part of a very large connected component, it doesn't necessarily have to be separate. But if there's an eigenmode which is entirely localized on that tree, then it doesn't matter if it's connected to the rest of the graph or not, you're still going to see it contributing to the density of states. So,
in fact, how big matrices could you deal with?
So the computation time, it depends how you're doing it. So belief propagation, essentially you're doing simulations in the infinite volume limit.
Propagation, perhaps not. Population dynamics.
Sorry, my mistake. Yes, population dynamics, yes.
But still you treat matrices, so what is
if you do these equations not for the variances of the finite instance,
but for deltas,
but for the probability distribution of the variances, you can do it in the infinite system limit.
Because you already impose self-consistency. In this sense. So you just solve it. Okay, I see.
So we say we're in an ensemble in which this self-consistency applies, then we can take the infinite volume limit, then we can do simulations.
Then natural question is, of course, to try to study localization on this. This
can be done.
And for the belief propagation, the other technique, so that computation time grows linearly with matrix size. So you can do much, much larger than you could feasibly do for direct diagonalization.
I know that to see localization effects, basically what you should remember that this is a tree, and therefore logarithms will be big numbers. So it's
that's true. That's very true.
Minimum 2 to 30 or something like this, which is million.
Exactly. Yeah. So it's very difficult to test.
Yes. Yeah. That's why I thought that probably your method had
in the ensemble way doing it, you see localization. Again, I mean, I don't have proof, but the evidence is.
So I would like to ask whether you expect the answers for these ensembles you studied and the trees for which this cavity method is exact.
Yeah.
Whether you actually expect in some limit that you get exactly the same answer.
Yes, yeah.
And that's the
In
answer.
the
is
tree
yes.
limit, in the tree limit it will
Yeah.
be, because these are precisely the same equation that people use in the trees, starting from Abu
Yeah.
Chakra, Taulis, and Anderson. These are just derived by different methods, but these are the same equation. You can write them just operating with green functions and using tree structure and writing this self-consistency equation.
Yep.
First I did not read, but when they were written, they are.
So in what limit are these things the same? I mean, I don't quite.
If you just derive, you see, if you just take green function, impose tree loopless structure of your
Yes.
graph,
Yes.
write then iteration
Yeah,
for
yeah.
this self-engine,
Yes.
but then impose that it's self-consistent. So you are very far from boundary. So you just have self-consistency equation. This is the equation that were written for us. By this is essence of cavity method, if I understand correctly.
And that is exact.
That is exact in which sense? In the same sense as yes, I can say that they're exact.
I mean, it must
I
be
mean-
sparse, some
Yes.
limit of you guys.
But this is precisely. You see, there won't be trees if it's in they're exact in the limit when it's if you just put them on a tree, they're exact.
Yes.
This is not-
This I
Right,
understand.
but we don't start from a tree.
That's right. That's my question.
But I understand. That's not from any matrix.
Yeah, but say this is imagine a Nerdos-Rainey random graph then,
Yes.
and you think how long the loops are in that.
Yes.
And as you grow system size to infinity, the loops get extremely long, and we can ignore their contribution.
But that's the question. Can
Yeah.
you ignore the contribution?
This is
Yes.
not, no.
This is what I
No, I think
You
this
saying that?
mean. This is
I'd
what I'm
say yes.
asking mathematically.
No, I think this situation is, I mean, basically what Bray and Rogers did,
Yeah.
in a sort of showing that they have an equation which is in replica symmetry, and you derived it using supersymmetric method. There is meanwhile, there are
Yes.
rigorous results that this equation is a correct
First,
description.
they are not rigorous. They are analytic, but they are not rigorous. And the essence of the method that something is done in saddle point approximation. If we believe that this is done,
There are different papers, Kubunchny and company.
no,
who claim that
then only in some regime they are I mean, it's not literally the same. So not this self-consistent equation in full.
Okay,
But okay, I think that this is correct, but no proof.
So if you can think about this.
You would say that in some limit, it really is exact.
Okay, wait. This is seen from
I understand
equations.
that- I
If we
understand-
believe if we believe in saddle point approximation at some point, we are done. Equations are the same as for trees. But if we, I mean, okay, for mathematician, we should justify this saddle point approximation.
Another way you can derive the exact same equations is to think about self-return walks to a site and relate the covariance matrix to weights of self-return walks. And then in terms of taking the infinite volume limit and looking at the lengths of loops, if the loops are long enough, you can truncate the expansion at a certain point and you'll see that the error doesn't grow. So in this sense, you can see that the contribution from very long loops is irrelevant.
To some extent. Really, to prove it, I think it.
I don't know if a rigorous this
I
is.
think that people
Yeah,
try to
same
consider this
problem.
rigorously in that paper that you mentioned, Karunji with some collaborators. They arrived to some meaningful results, but not in full. It was not full justification.
I mean, if I were to look at eigenvalue statistics, for example,
Right.
for such a system, and I would look at it on the tree, and I would look at it on these systems, would you expect there to be the same, exactly the same?
There is one important thing which was not mentioned here. When you consider really algorithm of generating sparse matrices, there is one nuisance which in fact, there is advantage in comparison with trees and disadvantage. Advantage is that here there is no this artificial boundary which dominates.
Right.
Yes, this is advantage,
Right.
serious one. But there is serious disadvantage. There are always disconnected. This was mentioned.
Yeah.
Disconnected clusters.
Yep.
You cannot avoid them. You should somehow sort them
Don't
out.
away.
Right? Because they will dominate many things. You can easily mistake them for localization, for example, because they are finite size. And they will, if you just get rid of them, then the rest, infinite cluster, will be like a tree with statistic. People, in fact, did it also numerically. There was a group in Israel, Berkovitz, I think. They did very nice simulations of this, and they found many. I mean, they found some spectral transition and all that we would expect. but it's not trivial. This is really a problem. Analytically,
I have
also.
some specific questions, but we'll hold it for later.
Okay.
All right, let's call it a day. Let's call it a week. Have fun in Cambridge over the weekend. Don't fall in the river if you go punting. Come back refreshed on Monday.
And thank the speaker.
And thank you, speaker.